Paradise Inn, welcome to our evening program here tonight. Tonight is a very special night. We've got a very special guest here. So it is my great pleasure to introduce Allison Barto, the project manager for the James Webb Space Telescope at Ball Aerospace. Allison's been working for 20 years doing astronomical telescope and instrumentation. She's worked on the Hubble Space Telescope. I'm sure you've heard of that. And she also manages the Ball Aerospace contribution to the Large Synoptic Space Telescope in Chile. So we're really excited to have her here tonight to talk to us about James Webb and all the stuff going on with that telescope, as well as talk a little bit about how she became interested in all of this. There's a fun connection to Mount Rainier. So without further ado, we'd like to welcome Allison Barto.
So I'm so excited to be here with you guys, and thank you for coming down to talk a little bit about space. Unfortunately, we can't observe it ourselves tonight, but we can talk about some telescopes we make that don't have to worry about the weather. So to start out with, if anybody tweets and all of that, here you can follow the telescope online. I came to be here because I grew up in the Seattle area. So I don't know where people are from. Who here is from Washington? A lot. Most people. Who is from out of state? Excellent. I got lots of multiple hands. All right, where are the farthest people are from? Maryland. Excellent. Our telescope is based out of Maryland at the Goddard Space Flight Center. Anyone else? Maryland? Florida. Florida. That's pretty good. That's a bit of a drive. Fly. So I came from Colorado, so I'm a little bit away from home as well, but I grew up here in Seattle, and I grew up coming to Mount Rainier on my summer vacations, and most every summer we would spend 2 weeks here at the mountain. And we would camp at a Hanukkah, and every night we would go to the ranger programs. You can learn so much about the park and its history and the people here, and that really inspired me in many ways. It was part of who I was growing up. So there's me, probably about 12 or so. I had a great picture of me in diapers in a trailer, but it didn't photo as well. But I've been coming here for a really long time, and a couple of years before this photo was taken, I was at a ranger talk in Hanukkah, and after that talk we had the amazing coincidence of a clear sky, and I've learned today I had to have both a clear sky, a new moon, and it was a Saturday, and that meant that Jim Ross, standing right over there, was going to give the evening star talk. And so after the night program, we all went back to our campsites, got our cars, got our blankets, and snaked up the mountain to a clear viewpoint where Jim gave us a star talk talking both about the constellations and the stories of what we saw in the sky and how people have imagined themselves and their interaction with the sky for millennia, as well as telling us a little bit about the science. And right after that talk, I said, oh my gosh, this is amazing. I have to do that. And I decided then that I wanted to go into astronomy. So getting to come back today, this is me with Jim, is really an incredible homecoming, if you will, because I've really come full circle now. I grew up, I came into my business because of Mount Rainier National Park, and so I'm so happy to be able to be here again telling you guys about the night sky. So, thank you. Over there. And so, question I like people to think about when we start talking about this telescope is, what do you think of when you think of space? For me, I think of this, the stars above Mount Rainier, because that's how I came to know space. To sit outside, I was usually here during one of the meteor showers, and just look up at the stars. Now, after that fateful evening, I got more interested in astronomy, I got a telescope. I joined a local amateur astronomy association. I would spend my summers going to Table Mountain. Maybe there's some people here who've been to Table Mountain. We've got Yes back there, where several hundred people come to Eastern Washington and all set their telescopes up. And this was amazing. I was able to look through huge telescopes. I remember a 32-inch mirror that someone had ground themselves by hand. And I got more and more interested in this. And now I get to build really, really big telescopes. That's a picture of me with the Webb telescope back here in the clean room at Goddard Space Flight Center. You can see it's folded up a little bit, and we'll talk about why it does that in a second. So, back to that question, what do we think of when we think of space? For thousands and thousands of years, this is what everybody thought of when they thought about the night sky. And then, this man came along. Anyone know who this is? Galileo. Excellent. Galileo, a little over 400 years ago, made the first telescope, pointed it to the sky, and found all sorts of things that were not supposed to be there. He looked at the moon, and there were mountains on it. It was supposed to be a perfect sphere. Everyone knew everything in the sky was a perfect sphere. He looked and saw moons orbiting around other planets. Again, this was impossible. We knew that everything orbited around the Earth. So it was really the advent of the telescope that started changing our relationship with the sky and with our place in the world and the universe. A little bit after Galileo, Newton invented a different type of telescope, a reflecting telescope. Galileo's telescope used lenses to refract the light, much like a pirate spy scope. And Newton changed that. Instead of using a lens to refract the light, he had a curved mirror so that he could bounce the light back and forth while he focused it, and that shortened the size of the telescope. This is important for us, and we'll find out in a second why. So with these two inventions, the race to learn more about the sky began. Because fundamentally, trying to understand our place in the universe is what we've done since the beginning of time. We wonder as humans and try to understand our place and our surroundings. And here we had a way to investigate more than we could before. So we started building larger and larger telescopes. You can see the Yerkes up here. This is a refractor, one of the last really large refractors built. Then we started building larger telescopes. Here's the 100-inch reflector at Mount Wilson and the Palomar 200-inch reflector. Now this is kind of fun. It's hard to see from where you are, but if anyone notices here, that's a person. So when we had these telescopes, first all we could do was look through them and make drawings like we saw from Galileo. Then we started to take photographs. But of course here, we couldn't just attach our camera to the telescope like we do today. The camera in there had to have somebody replace the glass slides. So we had to put the glass frames in for every photo, and he rode around all night like that. And there's still many people that work in astronomy today that spent time riding around in those cages all night. But we have a problem with these large telescopes. We made them larger and larger, but on the ground, there's still only so much we can see. The light has to go through the atmosphere, and so that distorts it a little bit and blurs our images just a little bit. Additionally, not all light makes it down to Earth because of our atmosphere. So this picture here shows what wavelengths of light make it to the Earth. So here you see our visible light spectrum, and the fact that it goes all the way down to the bottom is showing you that it gets to the ground. These other wavelengths, gamma rays, X-rays, ultraviolet, that gets absorbed by the constituents of our atmosphere. We see that as well in the infrared, little spiky areas, longer infrared here. Radio waves make it down, that's how we communicate with radio. But longer than that also is blocked. This is because of the way the light is absorbed by our atmosphere. So if we want to understand what's going on in space in these other wavelengths, we need to put a telescope above the atmosphere. NASA came up with a program of 4 great observatories to do this. We had the Compton Gamma Ray Explorer, the Chandra X-ray, we had Spitzer in the infrared, and then the one that we all know well, the Hubble Space Telescope in the ultraviolet and visible. And now these telescopes were first conceived, the idea of putting a telescope in space was first conceived by Lyman Spitzer back in 1946. This was early days of rocketry, long before we had the capability to do this sort of thing. And early images of the Hubble, ideas of what the space telescope, like the Hubble Space Telescope would look like, actually have an astronaut up there who had to ride along with the telescope the whole time. And why was he there? To replace those glass plates. But then we had to worry if this astronaut's in there trying to replace the glass slates, well, what's that going to do, you know, in zero gravity to the pointing of the telescope, and how can we control that? Well, luckily, technology came along and CCDs were invented, and then finally we had what we needed to make a robotic facility in space to do astronomy. And because of Hubble, now if I ask people who are younger than about 30 what they think of when they think of space, they probably don't think of that other image. They probably think of this, or this, or this. Hubble has fundamentally changed not only our understanding of space, but also our cultural relationship with space. This is what these amazing machines can do. But even with all we've learned from Hubble over the last 28 years, we still have a lot of questions. Just like when Galileo pointed his first telescope upward, he saw some things he didn't expect, but couldn't quite learn as much as he wanted, and he still had more questions. So we still have that, and so we need to build new instruments to help us answer these questions. For example, when Hubble was launched, we didn't know that there was a black hole at the center of every galaxy. It wasn't until about 25 years ago that we started being able to find planets around other stars outside of our solar system. All of this is new science that didn't exist when we were designing Hubble in the 1970s. So the questions that we still have today that we want to understand the answers to are really questions of origins, which is really what we're all seeking as humans, right? Understanding origins. The origins questions we have with the Webb telescope are understanding how galaxies form. When we look back at early galaxies, they kind of look blobby. And we look at the galaxies of today, and they're these beautiful spiral structures. So we want to understand that evolution. This telescope is designed to see the very first generation of luminous objects after the Big Bang. We're going to look back in time over 13.5 billion years to see that light. We also want to understand how stars form. How do the protoplanetary dust disks around those coalesce into planets? Does that always happen? Does it always happen in the same way? What do planetary systems usually look like? These are all questions we have. And then finally, we want to be able to look to see how common might life be in our galaxy. When we look at these other solar systems, can we look at planets and find signatures of life? We want to look for signatures like water, carbon dioxide, methane, byproducts, and constituents that we think we need for life. So with those questions in mind, we developed this idea to build the James Webb Space Telescope. This is built by NASA out of Goddard Space Flight Center in Maryland, and it is an international project. The European Space Agency is contributing science cameras and a launch vehicle. The Canadian Space Agency is also contributing science cameras, and here in the US, we have companies across the country who are building the observatory itself. And to build this observatory takes an amazing amount of time. We've been working on this since 2002. And what you see here is the route that a single mirror took during its manufacturing process, back and forth across the country. until it was finally in its final form. It seems really complicated. I mean, why would you do that, right? And why does this telescope look the way it does? I mean, if you think about what I just showed you, it doesn't look like a normal telescope, right? There's no big tube. Why does it look the way it does? Well, fundamentally, whenever we design a telescope or any other type of sensor that scientists use to understand more about our world or our universe, we go through the same process. We start with a science question, and that really dictates what telescope or other device ends up looking like. So what I wanted to do tonight is kind of walk through how we do that. How do we get from these fundamental, really big, amorphous feeling questions to about the universe and how it works, to deciding to build this thing. So the first question we have is this goal to see really faint objects. If we want to see that first generation of luminous objects, light that's been traveling to us across the universe for 13.5 billion years, that's really faint. So, what do we do to see faint objects? We need a really large mirror. Now, why do we need a large mirror to see faint objects? First, just a quick sense of scale. This is the Hubble Space Telescope mirror. It's about 8 feet in diameter. And here are just 2 of the 18 segments that make up the James Webb Space Telescope mirror, which is about 21 to 22 feet in diameter. So why is it that this big mirror is what we need? Great analogy to think of this is, imagine in your backyard, you left out that glass and a little pool. And they're both out in your backyard, and overnight it rains an inch. Both of those are going to have 1 inch of water in them. However, the volume of water in the pool is going to be much larger than the volume of water that you've collected in that cup. Well, telescopes work the same way with light. So the larger the mirror that we make, the more photons we're going to be collecting from these distant faint objects. So we need to make a really large mirror. Now this is where it starts to get really fun, and the engineering challenge collides with the science challenge. So this seems pretty straightforward, right? We want to see faint objects, we make a large mirror. This is our large mirror. You can see technician right here, another one right there. This is fully assembled in the clean room at Goddard. It's a pretty big mirror. That should serve our purposes. However, now we start coming up with our engineering challenges, which is, doesn't fit in a rocket. So it's great, we have this easy way to collect a lot of photons, we just make the mirror bigger. Unfortunately, the rockets are only so big, and it's really hard to launch a lot of mass off of Earth. So we have a solution, we just fold it up. That seems pretty straightforward. So we fold our telescope up to fit it into the launch rocket. And then while we are on our way to our final destination, about 1 million miles away, we robotically unfold the entire telescope. Lights. All right. So then we have another problem. We've launched, we unfold, but launch is really, really violent. Here is one of our mirrors undergoing vibration testing to see the kinds of loads that it's going to experience when it launches. You probably wouldn't do that with most bathroom mirrors you have and think it's going to survive. So we have to make sure that we can survive launch. But then we have another problem, just surviving isn't good enough. We saw before that the mirror, the whole big mirror, was made up of a bunch of smaller mirrors so that we could fold it up. However, what happens is we launch it, and now our mirror is going to look like this, because you cannot keep all of those mirrors precisely aligned through that crazy violent shaking. So we get up there, and, all right, we're not taking an image of a person. Our image is going to look more like this. Now you might look at that and say, great, it looks like you're seeing a bunch of galaxies out there. In fact, we're seeing 18. That number ring a bell? We have 18 mirrors. This is actually a picture of a single star viewed in 18 misaligned, out of focus mirror segments. That's what we're going to see when we first launch, because you cannot hold all those mirrors to that shaping that precisely. So clearly this is not going to work because we are going to have some really bad interpretations of what we think is out there in space if those are our images. So to solve that problem, we created what we call an active telescope, where we can move each of those mirror segments around to get them in alignment. So we go and we take a bunch of pictures, we find all these 18 different spots in the sky, and then, how do you think we figure out which spot goes with which image? Any ideas? Someone's got to have a guess. All right, you guys are probably all thinking this. We just tilt one and see which spot moves. It's just that easy. It's not rocket science. We tilt each mirror, and we look for changes. So here we've tilted one, and we could see in one image it was here, and the next image it was over there. So we know that this little spot corresponds to the mirror I just tilted. So we go through and we do that for every single mirror segment so we can find them all. And then once we find them, we identify them, we pull them into a formation that's easy for us to think about, and then we go through a process where we can look at their images from our cameras, and based on this we can figure out how we want to align and move them around so that eventually they form a nice image in the center. And we do all of that moving with what we call actuators on the backs of the mirrors. So these are motors that can move our mirrors. And we have 7 motors on the back of each of the 18 mirror segments so that we can move the mirror in rigid body, so we can move its position this way and sideways, and we can clock it like this and tilt it. And then we also have another actuator where we can actually change the curvature of each mirror segment as well, because we need all the curvatures to match and all of the segments to be lined up so that these 18 individual mirrors act like one large telescope. And we have to do this really precisely. We have to move each of these mirrors in position to within about 7 nanometers of its neighbor. So imagine a piece of paper. A piece of paper is about 100 to 200,000 nanometers thick. And our actuators move about 7 nanometers at a time. Very precise control. Okay, so this is pretty good. We have figured out how to collect light to see faint objects, right? Remember, this whole story here started with this one desire. I want to see faint things from space, right? So we built a big telescope. We figured out how to break it and fold it up. We figured out how to rebuild the telescope once we launch it into space. So that's pretty good. But we have some other scientific questions that we also need to answer. So we want to observe star birth and protoplanetary systems. Here is a beautiful picture from the Hubble Space Telescope of a star-forming region. Well, we can't see where the stars are being born because this is all cold dust. However, if we look at a different wavelength, this is what we see. Same field of view, looking in the infrared instead of in the visible light. So if we look in the infrared, we're going to be able to see through that cold dust to the warm object inside. We also have a goal to see signatures of life. Now remember, before we talked about our atmosphere making it hard to see all the wavelengths of light that we'd like to study because it absorbs that light. Well, conveniently, other planets' atmospheres are going to do the same thing. So what we do is we look at starlight passing through the atmospheres of these extrasolar planets. And when it passes through their atmospheres, it's going to absorb light at certain wavelengths depending on what's in that atmosphere. And so if we do this, we can learn what kind of chemicals make up their atmosphere. And for the very same reasons that we cannot observe in the infrared on the ground, that's the same reason we want to look in the infrared when we're looking at other planets. Because as far as we know, life requires water. We also know that the constituents and the relative quantities of those in our atmosphere change from before there was life on Earth to after there was life. So if we see certain ratios of these constituents, we have a pretty good idea that there's probably biological work going on that planet. So here you see, this shows a number of different constituents that we want for life: water, carbon dioxide, we have methane, oxygen, and wherever these peaks are, these are where they will show signatures in the infrared. So infrared is anything larger than one micron or so on this chart. So we want to be able to look in that region so that we can look for those same sort of lumps when we look at their atmospheres to understand if there's any sort of biological activity going on. All right, so infrared helps us there too. And then finally, the next question was looking for that very first generation of stars. And to do that, we need to be able to look back in time. Now, start with this. First, we need to look back in time. How do you look back in time? Well, everything takes time to travel, right? If I have an idea, and I think, oh my gosh, I need to share this idea with Jim, it's going to take me some amount of time to walk over to Jim and tell him. So he doesn't get my idea until I've gotten to him. The same thing happens with light. It takes some time for light to travel through the universe. So when we're looking at light from the sun, it actually left the sun a few minutes ago. As we go through space, those distances just get larger. So if there was an object that emitted its light, that we're seeing, that emitted its light a few million years ago, that we know it's a few million years old when we see its light. So we need to look back in time, but something happens to the light when it's traveling. Now, let's see here. All right, gotta demonstrate this one. Okay, so here's my universe. This is my universe. And in my universe, there is, don't worry, it's gonna get easier to see in a second. There's a little galaxy right there, and it's emitting light. Now, my daughter's gonna help me demonstrate this. This is Treviana. She is the same age I was when Jim gave me the star talk. All right, you gotta blow it up, facing that way, so that they can sideways. There you go, like that. Okay, so stop there for a second. As the universe expands, because it's always expanding, the light expands with it, because it is the same. So as she keeps blowing this up, notice that the distance between these little waves of light traveling from my galaxy to my guy with the telescope, they're getting farther and farther apart. As space is expanding, as the universe expands, it stretches the light waves with it. This is called redshift. You can stop there before it explodes. Thank you. That was pretty good. Right, so we saw that stretching. This is called redshift because blue light has a shorter wavelength than red light. So light that was emitted from something in the visible light, as it expands, that same signature is going to move into the infrared as that light wave gets stretched. So to look at things we look at nearby in the visible, the kind of pictures we take with Hubble, if we want to look at that same thing from a galaxy that's 13 billion light years away, we need to look at the infrared because those same signatures will have shifted. So for all these science goals, we need to look at infrared wavelengths. I know you need to, yeah. All right. Okay, so we still need to observe in the infrared. Now we have a problem with this. Can anyone think of when they've heard of infrared being used? What you normally might hear infrared referred to? Yes. Thermometers can use infrared, absolutely, because infrared sees heat. Also, military night vision goggles use infrared. So the problem is that everything warm emits in the infrared. You and I do, we show up in night vision goggles, we show up on your infrared thermometer. And so just like we can see through the cold sky, through the cold dust to the warm objects underneath, if we look in the infrared, you can see the person through things. So what if our telescope is warm? Well, if our whole telescope is warm, when we go to try to see these faint objects, we're not going to see the faint object, we're just going to see the glow of our telescope. So now we've got to figure out how to keep this whole telescope really cold if we want to see these faint infrared signals. We do this with two things. The first is our orbit. We go to an orbit called the second Lagrange point. Complicated thing, but basically we sit out here. Here's the sun, here's the Earth, Earth's orbit, and out here is where we put our telescope. And we orbit around the sun with the Earth. So the Earth, the Moon, and the Sun are always kind of on one side of us, and dark space is always on the other side of us. This helps keep us cool because we're able to essentially put up a parasol to block out the hot things so that we stay shaded. So we have this large sun shield that's about the size of a tennis court. And this sun shield, made of 5 layers, is able to reduce the temperature from this side of the telescope, the hot side that looks at the sun and Earth, to the cold side. We reduce the temperature by about 500 degrees. And we end up at only about 50 Kelvin on the cold side. It's around negative 400 degrees Fahrenheit, give or take. Extremely cold, so that we don't block our faint signals. Okay, so this is good, right? We knew we wanted to look at the infrared. We figured out that if we're in the infrared and we're warm, we won't be able to see what we want, so we cooled the telescope down. We figured out how to do that. There's always still another problem. So many standard materials change their shape over different temperatures. If you think about taking a glass of jam out of the refrigerator and you're trying to unscrew the top, it doesn't unscrew very well, and then you put it under the hot water. What you're doing is that the rate at which the metal lid expands in the heat is faster than the rate at which the glass itself of the jar would expand in the heat. And so that's why you can then get that jar top off. Well, we have to worry about the same thing here because we're going to cool this whole telescope down many hundreds of degrees, and we need it to work like a good telescope. So to solve this problem, we made our telescopes out of a material called beryllium. Beryllium is a metal. It starts in Utah, where we mine it, and create a very pure beryllium powder. And then we take that powder and put it into a big can and heat it up and press on it, and it fuses it into a solid. So we get a solid piece of beryllium that creates 2 of these blanks that we make our mirror out of. Now, the beryllium gives us a couple good properties. I'm going to talk about its property with the cold in a second, which is why we said we used it. The other thing that's great about it is that we can lightweight it a lot. So you can kind of see if this picture is better. We are able to machine all these pockets out of the backside because it's also hard to launch a lot of weight. Each of these pieces of beryllium, they're about this tall, about this big. When they start, when they're solid, they weigh around 500 pounds. And then we remove, if you imagine 18 times 500 pounds, plus all the rest of the structure, we just wouldn't get off the ground. But we remove over 90% of the material, so they weigh only around 50 pounds when we're done with them. So you or I could just pick one of these up. Beryllium is extremely strong, and it lets us remove this much of the material, which is very good for trying to launch something into space. But the other great thing about beryllium is that when it's at really cold temperatures, it doesn't change its shape very much. So most normal materials we use are pretty good about being stable at room temperature, right? If you've got your countertop on your metal table, and it doesn't matter if it's 80 degrees out or 50 degrees out, the table's still basically at the same height, right? But those same materials, once you get them really cold and they're down at 50 Kelvin, they start changing shape really rapidly. And that would distort our mirrors and make the whole mirror look kind of like a funhouse mirror, right? You imagine looking at yourself in one of those warpy mirrors and you look all weird, and again, that would give us some strange impressions of what we're looking at in space. Beryllium is the opposite. It changes a lot in room temperature. It's very hard for us to measure these mirrors and see see how good their surface is at, inside a normal room. But when we cool them down, now they're rock solid. So we polish the mirrors, and then it's a little hard to see. There's a guy right there. See him? And he's helping guide this big stack of 6 of these mirrors into this cryovacuum facility at Marshall Space Flight Center. We have to take them all cold, and we measure when they cool down how they warp, because like I said, this material is going to warp a lot. So it warps a ton, and this picture, you want it all to be one color, right? It's showing all the lumps and bumps in the mirror, and you can see there's red spots, and there's blue spots, and there's everything in between, and every mirror warps a little bit differently. But luckily, because we use super pure beryllium, it does it consistently every time. So every time I cool it down, it's going to make exactly that shape. So obviously I can't have that in the final telescope, so I fix it by taking a cold, measuring that, and then anywhere where I see a bump in the mirror, it looks like it cools down and it goes like this. When I get warm again, I go polish a little hole in the mirror. And now the next time it cools down, it still wants to bump up in that spot in the middle, but it bumps up to flat. So I basically see every way it distorts, and then we polish the inverse of that into the mirror. And when we're done, it looks nice and flat. Now, I can tell you that this mirror has a 20 nanometer RMS surface finish, and that wouldn't make any sense to anybody. So let's talk about better terms. Again, nanometers are small numbers. If you were to imagine that this mirror was the size of the United States, we couldn't have a mountain or a valley larger than about 3 inches. That's how precisely smooth we have to create each of these mirrors. All right, finally, we coat them in gold because it's highly reflective in the infrared. And then we test them again to make sure they work. We like to test a lot. Okay, so essentially, we walked through all of our science problems, right? We needed to see faint objects, so we needed to make something big. We want to look in the infrared, so we need to make an observatory that can operate really cold. We did all this. A couple years ago, we finished assembling the telescope. So here you can see it put together with covers on the mirrors, and then we finally had the full telescope. Now, once we have a full telescope like this, we need to make sure it works, because a million miles away, where this is going, we can't go fix it. We've never sent astronauts that far. So we tested a lot. We folded the whole thing up and put it on a giant shaker table. So you remember what we saw in that one mirror bouncing up and down? We did that to the entire telescope. So here it's being lowered onto a giant table. We shake it in every axis. We also put it in a big acoustic chamber and subject it to sound because of the impact of the sound waves of the rocket launch. So we need to make sure it survives that. And then after that, last summer, we brought it down to the Johnson Space Center in Houston. And we went into this facility. This large vacuum chamber is about 7 to 8 stories tall. It was originally made to test the Apollo landers. You can see 2 people right there. This is a 40-foot diameter door. It's the largest single hinge door in the world. And we put a large cryo shroud in there so we could cool that whole thing down to 40 Kelvin. So we take out all the air, we cool it way down. We put our telescope inside. We did that first, obviously, then closed the door, pumped it down, cooled it down. It took about a month to cool this entire telescope down to get it stable. We reached our final stable point where we could do our testing to make sure it works the day Hurricane Harvey hit.
Oh, gee.
So we tested through Hurricane Harvey. People had to sleep at Johnson on air mattresses. We learned that if you buy air mattresses for people, you should also buy blankets. We had a couple trucks that were able to shuttle people back and forth, and we were able to test it and show that it was meeting all of its performance requirements, doing what it needed to do. Then we took another month to warm it all back up. Right now, the telescope is in California at Northrop Grumman. where it's going to get integrated to the spacecraft and the sun shield. So the spacecraft and the sun shield are going through the same testing that we did with the telescope. They're going to be shaken a whole bunch. They're going to go into a vacuum chamber. They don't need to go cold, but we need to go into a vacuum chamber, make sure all the electronics are working. And then we put the two pieces together, the telescope onto the spacecraft, and then we shake it again because we really want to make sure that it's definitely going to work. But we don't have any more optical testing to do. The telescope's all ready to go. So we're going to put the pieces together, and then once they're together, it goes onto a barge, and we ship it from Los Angeles through the Panama Canal to the northeastern side of South America to French Guiana, where we launch on an Ariane 5 launch vehicle. And then, once we launch, it takes us about a month to reach our final destination at that second Lagrange point. And these are all the deployments that happen along the way. We start with the deployment of the of the solar panels to get communication going within a few hours of launch. And within the first few days, we're doing these large deployments of the sun shield to get ourselves cooled down so that the telescope can start to reach its final temperatures. So it takes a little bit to get this entire sun shield size, tennis court size, 5-layer sun shield deployed, tensioned, the layers separated. Each layer rejects about 100 degrees. And then once that happens, we're able to deploy the secondary mirror, which you'll see swing down here in a second, and then the two sides of the primary mirror come out like a drop leaf table. And at that point, we're ready to start actually doing all of that precise alignment that I mentioned before. So it takes us about a month, as I said, to get to the second Lagrange point. It takes us about a month as well to do all those major deployments, and then it takes us another 5 months to cool all the way down and do all the final alignments. So 6 months after we launch, we will be ready to have first images and first light. So I hope that this kind of gave you a little bit of an appreciation. I think this is such an exciting program to really marry the science, which intrigues all of us as humans, with the engineering that it takes to actually build the machines to do this. And hopefully you can also gain a little bit of an understanding of how we go about this process. It's really, while there's a lot of complicated things we have to work out, it's really a pretty straightforward idea of how do we get from the science question we had to the building the design for the measurement device that we use. Thank you. I'm looking at my Park Service folks, so we have a little bit of time for questions if anyone has questions. Yes? Okay, the question is, will I be there when the rocket launches? I hope to be in French Guiana when the rocket launches. However, most of our team needs to be at the Space Telescope Science Institute in Baltimore to start receiving the signals, because that's where we operate the telescope from. So I'm hoping I'll be there, but most of us will be in Baltimore. Other questions? Yep.
Now, how far away is that Lagrange point from Earth?
Yeah, the Lagrange point is 1 million miles away. For comparison, the moon is about 200,000 miles away.
And how long do you expect this to be usable? The Hubble's been out for almost 30 years.
That's right. So Hubble has been around for a really long time. Now, the benefit of Hubble is that it was always designed to be serviced. It wasn't just luck that we were able to figure out how to fix it. We always planned to be able to remove science cameras and put new ones in. So when we did have to correct the optics of Hubble, we had a way to do that. This is not designed to be serviced because it's going really far away, and we don't have a capability today to send astronauts that far. It's designed for about a 5-year mission life, 5 to 6 years, with a 10-year goal. So I expect that it should last at least 10 years. We have satellites up there today that were designed for an 18-month mission that are still working 10 years later. We're limited by fuel because even though the second Lagrange point is a gravitationally stable location. It still requires some station keeping to keep ourselves pointed the right way. So that's ultimately what will run out. The only other consumable is one of our science cameras has to get even colder than the telescope. It has to get down to about 7 Kelvin. And so it has active cooling, like a refrigerator on board to keep it cold. And so at some point it will run out of its coolant as well. But the rest of the observatory doesn't need any active systems. Yeah?
What's an average day at work?
What's an average day at work? Well, so the great thing about aerospace engineering is that everything we do, pretty much, especially when you're working on these kind of projects, hasn't been done before. So there's not really an average, right? Sometimes it's, like everybody else at work, I sit in front of my computer a lot, I go to meetings, but then sometimes things happen that we don't expect, and you spend the next, several weeks chasing down crazy things that you never thought to think about before. So it can be anything, which is why I like it. Yes? It should be launched in 2021. I think I have a question back there. Yeah?
Why did you pick that particular Lagrange point?
Why that particular Lagrange point? So it's in a good location. So you want it to always keep the sun, the earth, and the moon on one side. So your other Lagrange points, you're either at an angle to the earth, so the earth and sun are separated, or you're in between the earth and the sun, so you have that problem. There's another on the far side, but then communication is hard. So we like this one. Other telescopes are up there as well. We like that spot for astronomy. Other questions? In the back.
How does gold react to rocks?
How does gold react to what?
The drop in temperature.
The drop in temperature. It's fine. Yeah, it cools down at a sufficiently similar rate. It not cools down, but its expansion is close enough to the rest of it that it's okay and it doesn't do weird things. But that's something we really need to worry about. You have a bunch of different types of materials up here. And if one material shrinks faster than another material, then you're going to get stresses in the system. So for example, to make sure our mirrors don't all distort, when we cool down, we have flexures, little places that let joints bend between all these different layers of structure, so that even though the structure might do something different than the mirror, it won't actually distort the surface of the mirror. Yes?
Did you guys test the difference between silver coating and gold coating?
Yeah, so the question is silver or gold. People are probably used to silver coating a lot of telescopes. That's a common coating. It is not, its reflectance for our wavelengths isn't quite as good. Yeah.
I had another question about the coating. You talked about to make the mirrors uniform, you have to do those divots to counteract the warping. So how do you make sure the gold coating on top is also uniform?
Yeah, so how do we make sure the gold coating on top is uniform? Because if it wasn't uniform, it might pull on the mirror in different ways or distort in different ways. When we apply these coatings, they're essentially atomized, right? It's atoms thick, distributed kind of in a haze, if you will. So we're able, and you very, very precisely control exactly how many atoms of material you let go, essentially. So if you were to take all of the gold from that 25 square meters of mirror surface and put it all together, it's about the size of a golf ball. So not a lot of gold. Other question? Yeah?
About how many people, all told, contribute to this project?
How many people contribute to the project? Okay, so I can't answer that question completely, other than to say thousands. As I mentioned before, there are people across the world that have been contributing to this program for over 2 decades. At Ball itself, where we make the mirrors, and this doesn't include all our subcontractors, the folks that actually make the beryllium powder, machine out the back of the mirror, polish the mirror, all of those were done at subcontractors. But just at Ball, we had over 1,200 individual people worked on the program. We've spent over 1,000 man years of our time on this program so far. And we're just one very small piece of it. So it's many thousands, probably tens of thousands of people have touched this program in some way. Yeah?
So as the information comes back, who has that? Is the information proprietary? Who gets access?
Right. How's that information shared? This telescope will be operated like Hubble is. So scientists can apply for observing time. And then there's a combination of if you have a specific observing plan that you want to go look at this one thing, you'll have so many months with that data before it's then public, so that you have first rights. There's also some portions of the plan that are general observing, so they will make that public immediately. But you can imagine, like we see Hubble images coming out and that sort of thing, you'll see the same kind of return into the public sphere from this telescope. Yeah? Yeah, how are the mirrors connected? So each of those mirrors is installed onto a large backplane, a strut structure that's made out of a carbon fiber composite material. So imagine some bicycles, right, or really good hiking poles, since we're in the national park, that kind of material, so light and strong. Yeah. Do you have another question? Yeah. What the budget was, yeah. So projects like this that take that many people over that many years are really large. The official budget that's been out there is about $8.8 billion. There's a cost cap of that. We don't have an exact budget today for the current plan, but it's like that a lot.
How do you get funding for that?
The funding comes from NASA, and we're a line item, congressional line item, because we're the top astrophysics priority. Yeah?
Is the rank order of objectives what you stated? What you stated?
Is the order of our scientific objectives what I stated in the order I stated? No. So what's interesting about a project like this is we started early studies to build what was then called the Next Generation Space Telescope in the mid-90s. So shortly after we got Hubble working really well. And we kind of had an idea of this is the science we wanted to do. Well, since then, we've discovered things like exoplanets. As I mentioned, that's a fundamental part of what we wanted to do, what we want to study here. We didn't know how to do that when we first started thinking about this telescope. Luckily, the design of this telescope will help us do a lot of that science. So the priorities change and shift as science progresses. Other questions? Yes?
Who is James Webb?
Who is James Webb? Yes.
After him?
Great question. Well, I always forget to just answer that immediately. Someone always asks, which is great. Most of our telescopes are named after famous astronomers like Hubble, who is James Webb. James Webb was an early administrator at NASA, and he was the first person who said, NASA should be more than just sending humans into space. We should also be doing science. So he really brought science to NASA. All right. Okay, I think that's probably about all. Thank you guys. I'll be around for Q&A.
All right, that was. Okay, it's not working. It's okay. That was really wonderful. If you're interested in continuing your astronomical night with our Night Skies crew, unfortunately, we are unable to do our telescope program for obvious weather-related reasons. But we do have our crew set up in the back there if you want to come chat with us about astronomy, make a star finder for those clear nights you might have. We'll be set up in the back there. If you're around tomorrow, our first ranger program of the day will be our Discovery Walk in Paradise with Ranger Kayla. So that'll be at 10 a.m. at the flagpole. And I hope everyone has a great evening.
Thank you.